Hello everyone, this is going to be the lab report for the 5th lab in the Georgia Institute of Technology Introductory Physics Coursera MOOC. In this lab I'm going to be modeling the orbits of planets around the Sun, and I'm going to be looking to figure out, to estimate accurately the amount of time it takes for 4 of the planets in the solar system, the 4 inner planets, to make full revolutions around the Sun. So just a brief introduction. So the orbits of planets in our solar system are remarkably simple and stable physical phenomena. The configuration of the orbits in our solar system stays stable for up to 200 million years. And the orbit of planets around our Sun reflects fundamental physics principles, and it was through the development, through his thought experiment in 1687, his orbital canon, that Newton first came up with the concept of the universal law of gravitation, the idea that of the universality of gravitational forces that objects exert on each other. And our knowledge of the orbital motion of celestial bodies in our solar system throughout space, it comes from our ability to use physics principles to extrapolate from limited information, and that's what we're going to be doing here. So that's exciting. So just to lay out our goals, specifically we want to accurately predict the length of a year, a day, and month on Earth, as well as finding year length for the 4 rocky inner planets, Mercury, Venus, Earth, Mars. We have position, mass, and velocity data on the 4 planets, and we'll assume that the net force on the planets is equal to just the gravitational force of the Sun, and we'll also be modeling these planets' orbits as perfect circles, non-elliptical, eccentricity of 0. We'll get to those assumptions a little later on, talk about what effect that might have. So our initial information, or starting information, like I said, we have data for each planet's mass in kilograms, its mean orbital velocity, converting that to meters per second for our simulation, and the mean distance from the Sun throughout the planet's orbital path. We also include the mass of the Sun and the universal gravitation constant. Making the solar system its own closed system means that we've satisfied the energy principle, and we're modeling the masses as point particle, not real, and this is all two-dimensional. We're excluding any z dimension. So set up the visualization. We adjust the size of the objects. It's not to scale. The planets are too large by a couple powers of 10 relative to the Sun, but that's okay. It doesn't affect, the visualizations don't affect the physics of the model at all. Create trails to mark their paths, put the Sun at the origin. We input the mass and positional data, as well as the Sun's mass and g, and we set delta t and the time step. And we send the data to be written to a CSV. So now we're going to use the universal law of gravitation and Newton's second law to recalculate the net force, and then by extension the velocity and the position at each time interval, right? And we reset time and orbit trail visualization at each interval, and we calculate the planet's momentum, and we use it to find year length. So let's look at the model in action. There they are, the 4 inner planets. Got Mars out here, Earth, Venus, Mercury. And you can see here I've graphed the periods of the orbits. So the green period, that's Mercury, Venus, Earth, the blue, and Mars, the red. So we can see that all makes sense, that all checks out. And if we look at our results for these parameters, length of an Earth day, month, we have length of a day as sort of a standard. We have length of a Mars year in days, length of a Venus year in days, and length of a Mercury year in days. We see these match pretty closely. We have 687.69 for Mars, 224.8 for Venus, and 87.9 for Mercury. So let's talk about the sources of error in our model. You know, a number of factors can cause error in the simulation. These include the continual fluctuations in solar mass due to solar wind and radiation, and loss of solar mass. the effect of these solar emissions on planets' magnetospheres and the gravitational pull of all sorts of different things. You have asteroids and comets, small but close by, and the solar system isn't, we modeled it as a closed system, it's not necessarily. There's also the effect of other stars which are far away but of course very massive. And one notable factor this model did not take into account was interplanetary attractions. And so when I replaced the net force on our Earth object with a sum of the sun's gravitational force, we equated that F-grav to F-net in the syntax that I was showing you earlier. But when it add the sun's gravitational force to the gravitational forces of the 3 other planets, calculated the same way, I'll just add it together to make the net force on Earth. The difference for the number of days in a year was less than 0.04 days, so that's going to be a negligible effect on the Earth at least. Another factor we didn't take into account was the eccentricity of planets' orbits. Earth's orbit has a low eccentricity value, and Mars's orbit is more eccentric than Earth, but neither of them would really be, both of them are fairly close to a circular orbit, eccentricity of 0. Halley's Comet has a highly pronounced eccentricity of 0.96, you can see. Halley's Comet right here. So we would have a very hard time simulating the orbit of Halley's Comet using this simulation. All right, thanks for watching. Happy holidays.